Okay, so let's get started today. Um, so last time we talked about um, detecting whether the result of an acyclic join is empty, right? Today we're going to talk about how to compute um, the result of an acyclic join. Okay? So I'm going to use Q to represent an acyclic join. Okay, because of acyclicity. Um, if I say you have to give me a join tree, okay, and then you cannot deny my request, okay. So what is this join tree? Now remember, if you have Q, and then definitely you have a schema graph, okay. So this is schema graph, BE. Hope you still remember this. Okay. Um, so now remember, join is defined by a set of relations. Okay. Every relation defines a hyperedge here in this E. Okay. And if you look at this V, uh, that's essentially the union of all the hyperedges, right? Okay. So I'll use the term attribute to refer to each vertex in V. And a hyperedge is essentially just a set of attributes. Okay, so today I'm not going to repeat the whole notational system again. I did it twice already. Okay, so this G must be acyclic, okay, because Q has been named an acyclic join. So this T will have to exist. Okay, so join tree. Um, just to brush up your mind, this join tree has two properties. The first one is one-to-one. So that basically says every hyperedge here corresponds to a node in this join tree. Okay. The second thing is this join tree um, must have the connectedness property. Okay. Well, in order to demonstrate this, I'm going to give you a join tree right away. AB, AC, AD, and I say B, C, D, E. And then you got C, F, and CG. All right. Now that's a join tree. Um, so here, if I say how many relations there are in this join, then you should tell me four, four. Oh, sorry, so six. Okay, four plus two. Okay, six relations. If I say what are their schemas, what are the attributes in each relation, then you would say just look at the nodes, right? So here, this represents a relation with attributes A, B. This node here represents a relation with attributes B, C, D, E, et cetera, right? Okay, so I was talking about the connectedness property. Connectedness property essentially says that um, if you focus on any particular attribute, actually I realize this is not correct. This is AE, and then yeah. So if you look at any particular attribute, okay, so this is ACE, okay, yeah. So if you look at any particular attribute, just to correct this, okay, ACE, okay. Let's say C, and then if you say, okay, look at the nodes containing C, okay, so it will be AC, ACE. Um, let's say this is ACH. Just to make it more interesting, so that you don't have one relation contained by another. But AC will do just fine. Anyway, so if you look at C, right, look at the nodes containing C, it will be ACH, ACE, CF, and CG, right? So tell me, are they connected? Right, they are connected, right? So this is the connectedness property. And if I say look at A, right? Well, you would say, look, these are the four nodes. Are they connected? Yes, they are connected, right? Okay, so that's a join tree. Good. So today we will take such a join, and we want to compute the result. Okay. So the complexity that we will aim at is this. Okay. Um, so in order to define the complexity, I will first have to define the input size. Okay. So I have to do it in two steps. So for every relation, so R is a relation, and then we say the size of R uh, is basically how many integers you need in order to represent the tuples, right? So this is the number of tuples, okay, and times the schema of the relation, okay. So if you look at this is the number of integers required to represent all the tuples from the relation, right? So once again, the first row here, the first term here, this R size, right? This is the set size, right? So R is defined to be a set of tuples, and therefore this is like what I said. Now schema, so this is the set of attributes in R, right? The columns, right? So here, the size, so the number of attributes, and then that's the size of the relation. So the input size of this join is defined to be this. If you look at all the relations in the join, and then you simply add up their sizes. Okay, so this is the number of integers that you need in order to represent this relation. Now, what about the output size? The output size is defined in the same way. So this is simply the size of the output relation, and the output relation, according to our notational system, is this. Okay, so you take this Q, which is defined as a join, and if I say, hey, join Q, right? This is the result of the join, right? But that's a relation. Now remember, relation in, relation out, right? And then if I say what is the size of this relation, you know that's the output size. Okay, out, not output, out. Good. So today, the time complexity we will aim at is this. Okay, so this is the number of relations in this join, right? And then in plus out. All right, so this is what we're gonna get today. Okay, in plus out. Okay, times the number of relations in the join. Okay. All right. Let's interpret the result a little bit. Okay, so first of all, you can't say this is in polynomial time, because I'm going to follow up by asking you, hey, what is polynomial in what? So if you say this is polynomial in the input size, wrong. Why? Because this L can be exponential in the input size, right? The number of relations here is not necessarily a constant, right? So if you have a lot of relations here, you can see basically the output size can go up exponentially. Right? However, this is polynomial in the input size and the output size. Okay, so this is usually how people interpret this result in the polynomial domain. Okay, whenever they say acyclic joins, they are solvable in polynomial time, they are referring to both in and out. Okay, so this is one very important thing. Another very important thing is the situation where this Q has only a constant number of relations, which is true in practice. Okay, in practice, all right. I told you last time, 99, oh, that's too much. 90% okay, of the joins in practice are acyclic joins. And in practice, I mean, how large can this Q be, right? Let's just be realistic about it. Or even if it's 100, it's not really that big a deal from a theoretical point of view, right? So as long as it's a constant, and then the complexity will be very good. You see what I'm saying? It will be in plus L. So in plus L is absolutely the best you can do, instance optimal. Okay, it's not even worst case optimal, instance optimal, because no matter how smart you are, you have to read all the integers at least once, right? And even if you just want to output one tuple, you already take constant time. You see what I'm saying? So no matter how smart you are, you will need so much time to output all the results, right? So this will be absolutely optimal if Q is a constant. Okay. Now is a great time to introduce a few terms. Okay, the first term is query complexity in database theory. Okay, so in query complexity, basically you assume that every relation has a constant size. So it's exactly the opposite of what people care about in practice. Okay, so in this case, the number of relations can be arbitrarily large, and also the number of attributes can be arbitrarily large. Okay. Um, so in case you're wondering, hey, why should we care about query complexity? The answer is think about this three-set reduction that we talked about in this NP hardness proof, right? So that tells you that join is not really just for database systems. Okay, so joins are very expressive in the sense that they encapsulate a lot of problems that you know of. I mean, if you can encapsulate three set, it encapsulate a lot of stuff. All right. So if you still remember the reduction we built, okay, in three set, every relation has up to 7 tuples, right? So every relation has a constant size. So this is the query complexity. So basically, you worry about the dependence on the size of Q. Okay. Well, another uh, branch of database theory studies data complexity. Now, this is the practical branch. Okay, data complexity essentially says, this graph is a constant size. Okay, this graph is a constant size. You see what I'm saying? So basically, say the number of attributes you have is a constant, and also the number of hybrid edges you have is a constant. Okay, and therefore the size of Q is a constant. You see what I mean? So that's basically what we see in practice. Okay. And then you would say, how about I'm interested in both? Well, you are very courageous. Okay. And indeed, you can do that. So this is called combined complexity. Okay. So basically, you are saying, I don't assume the relation size to be a constant. I want something like this. This is basically a combined complexity result. Right? So this will be the strongest result in database field. Okay. Good. Now you already know that things are quite efficiently doable if you have acyclicity, right? So that's why, when we talk about acyclic queries, I always present things in the combined complexity mode, okay? But if you deal with arbitrary cyclic queries, things would go much more difficult, right? Unless you are able to prove NP is P. You don't really expect to solve any cyclic, you don't really expect to solve all cyclic queries in polynomial time, right? So as you will see, whenever people talk about cyclic queries, almost always, do they assume that do they consider data complexity? Okay, so that's what we're going to do down the road. Okay, so that will be several weeks down. Okay, and you guys don't have to come. Okay, so that's when we're going to talk about things like AGM bound, that kind of stuff. But the AGM bound strictly in data complexity. Okay, good. All right, that's very nice. Now let's talk about how to achieve this time complexity. Okay. Well, you're almost there, I would say, based on what we talked about last time. Okay. So in terms of theory, there will be one more important theorem. Okay. So this is the decomposability theorem. So this is basically the main takeaway from a theoretical point of view. Okay. So that's what I'm going to talk about first. After we're clear about that, we're going to talk about the algorithm itself. Actually, the algorithm, I would say, is not that surprising once you understand the decomposability theorem. So this algorithm is able to achieve this bound, and that's known as Yanakaki's algorithm. Somebody would say, oh, last time you said this emptiness algorithm is Yanakaki's algorithm, and this one is also Yanakaki's algorithm. Yes, that's correct. Okay, all right. Now, the first thing for today is to get a fully reduced John of the input. Is that all right? Is that all right? If you say you're not all right with that, well, I will have to teach you for another 60 minutes. Okay, because this is exactly what we talked about last time. All right. You can pay Q times in, basically. All right. So this is what we proved last time to convert everything into this is so-called um, fully reduced version. Okay, so just so you know what is fully reduced, right? Now, fully reduced basically says that every relation is very clean, it's minimal, it's actually minimum in the sense that it does not have any useless tuples. Okay, so you see all these things are in English, right? So let's put them in formal language. Okay, so Q is reduced, fully reduced, sorry. Fully reduced if the following is true. Okay, so if you look at the joint result, that's a relation, correct? That's a relation. Now, if you want to project it over the schema of any relation, now you get back that relation, and this holds true for all the relation in the joint. Okay, that was pretty fast, but if you could follow me, you're um, very good, with the notational system. All right. So this is the joint result. That's a big relation, wide relation. You take the projection over the schema of R, ACE, ACH, you get back the original relation. Okay. And if there is a tuple, okay, so let's say you have R, that's a relation, and U is a tuple inside the relation. If you see that, this join, U, so how did I define dangling tuple last time? I forgot how I spoke the language last time. Okay, let me see. If you join this queue, if you join this queue, okay. So today, I can I just take a quick look at my lecture notes, please? Oh, not here. This is there. Okay, thank you very much. That's exactly what. Yes, yes, and that's what I had in mind too. I just thought about that. I'm kidding. Thank you so much for saving my life. All right. So if you look at a relation and if you have a tuple inside this relation, however, um, if you look at this, um, like this R that so do the projection over the schema of R, right? So this is what I did in defining fully reduced. But this time, I say U is not there. And then this U is useless, right? So U is dangling, okay? So what is a fully reduced version? Fully reduced version says, okay, Q does not have to be fully reduced. However, I can always convert it to an equivalent join in terms of result, okay? And that equivalent join is fully reduced, okay? So this is essentially the problem. The problem we solved last time, okay? All right. So conceptually, if you say what is a fully reduced join or version of this Q, and then you need the dangling formalizations, and basically you say, okay, look at this procedural definition. Okay, so for every relation, whether a tuple is dangling or not, that's well defined, right? So if it's dangling, then you remove it. You keep removing dangling tuples until you have no more, right? So and then you get the fully reduced version of the query. Okay, so I hope everything's clear so far. All right, so you start with a Q, which can be any acyclic join. It doesn't have to be fully reduced, but you want to convert it to the fully reduced version of the join. All right, so from now on, I will assume we only have a fully reduced input. all right? Because you can always do this pre-processing, correct? Nice. Very nice. Okay. So just now, I can see you haven't passed out yet. By you haven't the you're not so confused yet. I can see. So I'm gonna take the chance to introduce this binary join result. Okay. So this binary join result basically says, let's say you have R1 joining R2. Okay, so it's a join with just two relations. All right. If I say, okay, I want you to solve the problem in so much time, this in is just for R1 and R, just for this join. Right? So basically, in it says, how many integers you need to represent R1 and R2, and out is how many integers you need to represent the join result. Okay. So if I say I want you to solve whatever binary join, in this complexity, are you able to do it? Well, I hope you are, because I'm not going to talk about it, because this is fairly rudimentary, right? So, sort and merge or binary search tree. There's so many things you can do, right? So what is this tilde here? Well, this big O tilde hides a factor, okay? Hides a factor that's probably not, that's basically logarithmic in the input size. You would say, okay, why are you being sloppy? Well, yes, I'm a little bit sloppy here, but that's such an insignificant factor. So I mean, it's almost as insignificant as the hidden constant here. Okay, hidden constant is big O1, right? I can also call you sloppy. Okay, why did you omit that constant, right? I want that constant, right? Yeah, sure, but it's going to take a lot of work. You see what I'm saying? I could have that log everywhere, but then people just don't care about it, right? Because we're talking about polynomial time level. You see what I mean? So in fact, from a theoretical point of view, n log n and n log to the power of 10n, that's pretty much the same. That's called near linear. All right. But still, if you can shave off some logs, that's still a good thing, right? But it's not going to be as significant as saying I go from n to the power of 1.00001 to n log n. You see what I'm saying? Because that's a polynomial time improvement. Good. All right, nice. So now I'm going to talk about this decomposability result. Okay. So this result, oops, what happens? Okay, so this result is something we need to design, actually not design, to bring out this final algorithm. Okay. Now, what I'm saying is, look at any node in the join tree, right? So this E, it has its subtree, okay, and it has its parent. I forgot to say you root the node. You root the join tree at an arbitrary node, okay, because join tree by default is just a tree. It's not a rooted tree, right? But you root it, okay. So you root this. So for example, here I have chosen CF to be the root. All right. Don't ask me why. If you do, I would say, it's you can choose another root. That would be okay. Just that the tree is going to look different. Okay. So if you ask me what is the purpose of rooting a tree, the purpose is now I can say AD is a child node of ACE. Before I was not able to say something like this. You see what I'm saying? So now I can say parents, I can say child nodes, that would make sense, right? Another thing that would make sense is, okay, so I can say something like, look at the subtree. Before it would take me a lot of effort to define a subtree, but now I can say something like, look at the subtree rooted at ACE. That would be perfectly clear. You see what I'm saying? All right, because in general, a subtree could be something like, AD, ACE, CF, as long as something connected, it's a subtree of a non-rooted tree. You see what I'm saying? But now I can say, look at the subtree rooted at ACE, and then there's only one possibility. You see what I mean? Because, rooted, right? So this is what I'm saying, all right? So you take an arbitrary node, this E, right? So I'm going to talk about the subtree rooted at E, okay? So as you will see, a very important concept here is the so-called subjoin. Subjoin. All right. So this is quite natural if you look at things from the following perspective, right? So look at this ACE, right? So if I look down, what do you see? You see how many relations? You see four relations. Okay. Now, what is the definition of a join? The definition of join is a set of relations. So I mean, whenever you have relation, you got to join, right? So if I say, okay, ACE, now look down, look at that join, things are perfectly clear, right? So this will be ACE, AD, AC, HAAD, etc., right? No, etc. Okay, so four relations. So here, I'm going to say, I'm going to use the notation QE. Q represents join, right? But I put a subscript here to refer to this subjoin. You see what I mean? So that should be clear. All right, good. Very nice. Okay, so now I'm going to ask you to look at the join result of this subjoin. That makes sense, right? This notation, right? Now you can feel the power of mathematics. Mathematics is a language, just like C++. Okay, if you speak the language, and then you can rely on its power. I haven't said a lot of things, but with this notation, you know exactly what I'm trying to say. It's a data basic, right? Okay, good. So you look at this, and remember this is a set of tuples, right? Okay. Now, I would say you look at this RE. Okay, so RE, in general, this is a relation whose schema is E. Okay. All right, so you look at this join result. All right, so that's one thing we're going to talk about. But we will also be talking about this RE. So this RE is the relation right here, right? So in my running example here, consider ACE. There's a relation there. And if I say the join result, and then it contains also attributes like, B, A, etc., B, D, etc. Okay, good. So now I say, okay, consider one tuple in this RE. All right. So for example, ACE. Now I want you to think about one particular role in this RCE relation. Is that all right? Okay. So let's drill into the subtree a little bit. Let's say this is E1, E2, and ET. Okay, each one of them has its own subtree. So I mean, so we zoom in a little bit. Okay, good. So here you can have ACE as E, and then now it will be T will be 3, right? So this is E1, this is E2, and this is E3. Is that all right? Good. Very nice. All right. Now each one of them also has its own subjoin, right? Okay. Now we're going to see a relationship between this subjoin of QE and the subjoins of the channels, okay, by way of an arbitrary tuple in R. Okay. So before I present the details, I want to give you a heads up about what you're going to see. Okay, so from the global perspective, it's not immediately clear unless you know where to look. Okay, unless you know where to look. It's not immediately clear there is a Cartesian product structure hidden in the mathematical structure of this acyclic joint computation problem. Okay, Cartesian product, right? Clearly, this is not Cartesian product. Okay, however, this is what you are going to see after all. Okay, you will see there is a Cartesian product structure hidden inside this acyclic joint, and that's basically the reason why a lot of things are easy, such as computing the joint result, counting the number of tuples in the joint result. If you want to count, you don't have the plus L term. Okay? And in the future, we're going to talk about sampling from the joint result. You can actually sample, in data complexity constant time. This is not something that's doable for cyclic joints. Okay, I give you a joint like this, you can pre-process the joint in linear time. And then I say, I don't want the entire joint result, okay? I just want an arbitrary, not arbitrary, a uniformly random sample from the join result without computing the full join. You compute the full join, that could be 1, 2, 3, 4, 5, 6. It could be n to the power of 6. But if I say I just want a uniformly random sample, right? So that's what they need for vector databases, right? You can actually do it in constant time. So you go from n to the power of 6 to constant. And all these things are made possible by this decomposability theorem that I'm going to present you, right? And this decomposability theorem is essentially Cartesian product. Now let's see. All right, so as you know, I have E here, so I'm just going to write things here. But this E corresponds to that E, all right? So now remember, E is a hyperedge, right? Just like hyperedge ACE, right? So E1 is also a hyperedge. So I'm going to say, this Xi, if this Xi is a set, X1 here, this is the intersection of these two hyperedges. Okay, so for example here, ACE and AB, what's the intersection? That's A, you see what I'm saying? So intuitively, this is how the subjoin AB, this is the little window, okay? Or for Chinese people, it's well, you see what I mean? Okay, it's a little window for a tuple inside this subjoin to see the world. Okay, so that's why the well, right? Okay. Let's look at every other child node, right? So you can compute such a window, right? So for actually for all these guys, it will be A. Okay, so that's a bit boring. So let's change the result a little bit. Let's say something like this. So that for CH, it's going to be C. All right. Yeah. Okay. Good. Very nice. Okay. So once again, to give you more intuition, how come you have a Cartesian product? Okay. So now you can look at the other parts of the subjoins of the children. Okay. Let's say B. Hey, B has nothing to do with any other part of the tree. You see what I'm saying? Okay, if you say, okay, even though B is not in ACE, B could be here, and then you have forgotten about connectedness. You see what I'm saying? So whatever you have about B is inside the subjoin. Okay, so from the parent's point of view, there's no B anymore. B is sort of like payload data. You see what I mean? Payload data is sort of like something piggybacked on A. All right. Same here, right? So this H is specific to this subjoin, and this D specific to the subjoin. All right. And therefore, if you look at these tuples, all right, once the common attributes, right, this A, C, are determined, and those tuples, you will see a Cartesian product later on. Okay. All right. So let's go into further details. Now, as I said, you have E. Look at the relation. You look at the tuple inside this relation. Now, I want you to think about the following child product procedure. Okay. So this child product procedure says I'm going to compute a Cartesian product. So that's why I have S times. Okay, this is not X, like Cartesian product symbol, right? So this is a set. Okay, I'm going to compute it eventually. Okay. So in the beginning, this is an empty set. Good. So for every I, right? So you define a set. All right. So for every I, you define this set as U. Let me give you the math, and then I'm going to explain. Okay. So this is the joint result of this Q EI. Okay. And for I from 1 to T. Okay. All right. So I'm going to explain. All right. So what is happening? Okay. So first of all, this part, even though it's a bit long, I think it should be perfectly understandable, right? So this is just the result of the subjoin for the child EI. Okay. That should be clear, right? Now, what is this? Well, this UXI says, okay, since I'm talking about subjoin, I try to be friendly to you. All right, so this U may carry some attributes that are not in the subjoin. All right, so let's get rid of that. All right, so how do you get rid of that? Well, you say we do the projection of this U over the common part. You see what I'm saying? Okay. So now if you think about what this gives you, this basically gives you all the tuples in the subjoin that are relevant to this U. Okay. So here is an example. Let's say ACE is this relation E that we're talking about, and then U is in this relation, right? You know this subjoin AB, right? Subjoin AB in this case is very simple, just the original relation, right? Okay, if I say this U, right? If I say, okay, now what tuples in AB are relevant to this U? And then, basically you would say, I take the A value of U, right? And then I look at which tuples in this AB can be joined together with this U. You see what I'm saying? Okay. So that's how you get a subset of the subjoin result, right? So this is Si, right? So you get S1, S2, S3 here. Okay, cool. Now let's look at the following. Okay, so for each V1, V2, to Vt in the Cartesian product of these SIs. You see what I'm saying? Okay. Now let's look at the power of math, right? So Si, the sets Si are clear now, right? So if you look at the Cartesian product, all right. So here it will be in my example, it would be basically, a subset of AB, Cartesian product with a subset of CH, Cartesian product with subset of AD. But all those subsets, they are related to one tuple in ACE. You see what I'm saying? Okay. All right, so this is to look at all the Cartesian products of these three relations. If you look at this T here is 3, right? Good. Now, watch carefully. Here, say add a U, John V1, John V2, John VT. Okay, so this is S times. Okay. Now this is the child product procedure. Okay. So I'm going to tell you what it does, but this is the procedure. Okay. So to explain, right? So let's say for the ACE here, I have a tuple. Let's say this tuple is 1, 2, 3, right? 1 for A, 2 for C, and V for 3. Okay. All right. Now, intuitively, you can imagine the following way to compute the part of the subjoin of ACE. When I talk about a subjoin of ACE, there are 4 relations here, right? You think about the following way to compute, the part of the subjoin result that is related to 1, 2, 3. Okay. And how do you do this? Well, you would say, okay, let's first do recursion. Okay, so you compute the full join result of AB. In this case, it will just be the relation, right? Then you compute CH and compute AD. Okay. But now you have got just 3 separate results, right? You have to somehow combine them. And that is the hard part. So I mean, that's the hard part. If you're not careful here, it would take you a lot of time combining all those results, right? Okay, good. But then the child product theorem says conceptually, there's a very easy way to combine these results. Okay, so the approach is this: you look at this 1, 2, 3. Okay, so use this 1, 2, 3 to filter the result from the first join. Okay, so you keep only those tuples in the first join, the part in the first join result that is related to 1, 2, 3. Okay, so in this particular case, it means the part of the result in AB whose A values are 1. Okay, and then Same thing, right? For CH, whose C value, whose C values are 2, etc. Right? Good. And now you have 3 subsets. You see what I'm saying? So the child product theorem essentially says, now you can take the Cartesian product of the subsets. Okay, take the Cartesian product of the subsets. So basically, you say, I just go ahead, I just combine them all. All right, combine them all. And then after combining, you get this V1 to VT, right? So why do you still have to join it with U itself, right? Why do you still have to join it with U itself? Well, this is because U has something like Y. You see what I'm saying? Okay, Y is not really in any of the subtrees, right? So Y is standing right here, right? And therefore, in order to get a tuple that has A, B, C, D, E, H, all these attributes, you have to do something like this. Okay, so this is essentially saying I'm making the tuple longer, right? Because you can see every input relation has just one single tuple, right? So this is essentially to make the tuple longer. Okay. So this is the child product procedure. Okay, good. Now, why is this correct? Okay, why is this correct, right? So this is basically the details of this decomposability theorem that I have. Okay, so today I will probably not prove it, at least not officially. In the seminar and maybe offline, I can discuss the proof with you. Okay, decomposability theorem. Okay, so this decomposability theorem tells you the following. Okay, tells you 3 things. First, if you look at this line here, okay, let's give them some numbers. 1, 2, 3, 4. Okay, line 4. Okay. There is a possibility that this could be empty. You see what I'm saying? Okay. Because if, let's say, U is 1, 2, 3, and V1 is having a different value on A, and then, this joint result will be empty. And then you will be adding nothing to this Cartesian product. You see what I mean? So the first statement of this theorem says every time, okay, I would say line 4 always adds a tuple to this Cartesian product. Always. It means there's always, this is never end. All right. This is important. Okay, because if this was not true, and then you won't be able to do counting. Okay, you won't be able to do a lot of things later, right? So now I can say, okay, 1, 2, 3, this U produces how many tuples in the subjoin of ACE. Now I can immediately do multiplication. You see what I'm saying? All right, so I simply look at the size of S1 to S1, S2, and S3, and then I take their sizes and multiply them. So this is the first thing. And also the second thing says line 4 never adds the same tuple twice to Sx. Okay, every time you execute line 4, a new tuple is being added to this Cartesian product. Okay, good. All right, now the last line here says, the last statement here says, okay, so if you look at U joining the result of the subjoin, okay, so if you look at this, so remember E is the relation where we have fixed, right? So this is the result of the subjoin. So if I say U natural join with this, then basically saying, what are the tuples in the result of this subjoin that are relevant to you, right? That are contributed to by this U, right? Okay. All right, so this is precisely this Cartesian product, right? So basically, this is what I told you about, right? So if you right? So I explained this bullet here with this 1, 2, 3, right? I said, okay, so you start from here and you want to compute the part of the subjoin that's relevant to 1, 2, 3. What do? You do this. Okay. Right. So this is a decomposability theorem. Today, I don't think I will have time to prove it. The proof is in the lecture notes. Okay, I can stay behind. I can discuss with you informally how to prove this. Okay, but should not be too difficult. Okay, it should not be too difficult. Okay, once people have pointed out for you what you are supposed to prove, and then a lot of people can do it. The hard part is pointing. You see what I'm saying? Okay. All right. Good. All right. Now let's utilize uh, this theorem to compute the join. Okay, to compute the join. All right. So let's again use this. Okay. So now let's look at the algorithm in general first, and then I'm going to utilize this example to illustrate it. Okay. The primitive here is a subjoin subroutine. Okay, so this y, as I explained, this y is a node in the join tree, right, or a hyperedge. All right, so here the goal of this subroutine is to find you the result of the subjoin of y. Okay, so the first thing is, what if y is a leaf? Right. Well, in this case, there's nothing to do. You see what I'm saying? You simply return this relation, right? So, for example, if E is AB, I say I want the subjoin. I would say, okay, sure. Nothing needs to be done, right? So just a relation AB, and here it is, right? So this is what it does, right? Okay. Well, else, and then let's think about this E. As an internal node, and without loss of generality, I can say it has T children, right? So something like this. Okay, good. All right. Now what do you do? This is what you do. First of all, uh, you do recursion. Okay. So you want to compute each subjoin. Simple, right? Simple. Okay. Very simple, right? So this is well defined, right? This is rigorous. You know what that means, right? Okay. And this is recursion, right? Okay. And then finally, you come back to E, right? Recursion is over, right? And then you simply return, RE. So that's the relation at E, right? You just join with everything else. Okay. And that's it. That's the algorithm. Okay. That's the algorithm. So if you look at this algorithm, it's not clear at all why this is correct, right? Okay. But hopefully now you have uh, the confidence to say that you can prove the correctness of this algorithm. It's not that hard. Okay, so just use the decomposability theorem. So one tiny little question here is how you are going to compute this thing here, right? This line 4, right? So this is done by simply doing binary joins. Okay, 2 at a time. Is what I mean. 2 at a time. So if you look at this, that spits out a join, right? Spits out a relation. Sorry, spits out a relation. Okay, so now you get a relation, and then this expression gets a little bit shorter, right? And then you use this relation to join with the next one, is what I'm saying, and et cetera, et cetera. So this is essentially binary join. Good. Now let's look at this running example, right? So this example is, I would use this example to illustrate the algorithm. The algorithm is extremely easy, right? So basically you say, okay, the first thing you want to do is ACE. Okay, you join ACE with AB, so that's one binary join. Now you get an intermediate relation, right? Use that relation to join with CH. Again, you get another intermediate relation. Use that relation to join with AD. All right, good. And then continuing, now you are done with the subjoin of ACE, by the way. So you have a relation which could be quite big. Use that relation to join with CF, and then finally that relation with CG. Okay, so that's the algorithm. Okay, this is Yanakagi's algorithm. Now let's talk about running time. Okay, let's talk about running time. So this running time, as I said, right? If you want to do binary, right? So if you join R1, R2, right? The running time is in plus L, right? I don't care about polynomial factors. And then another way to understand this in plus L is the following. So if you want to directly look at this in plus L, it will also work, okay? But there's another way to look at it, okay? So you can look at this in plus L as the total money you have to pay, right? This is your cost. And you can hold a view that you are going to amortize the cost over a lot of integers, okay? So that every integer is paying something for you, okay? So in particular, this in, I will amortize this part, this in, right, over all those integers in the input relations, right? So you can imagine this is interesting, right? So it's just like if this integer participates in this join, and then it's going to pay $1. You see what I'm saying? All right. And then in the end, you can just count, okay, how many dollars this integer has paid overall. You see what I'm saying? Okay. Anyway, so this out here, the same thing, right? You can charge this part over the output, right? So this is the output, the number of integers in the output relation, correct? So you can think about this as saying every value, every integer in the output relation pays $1 for the join. Okay, good. So if you hold this view, then it's almost immediate that the overall cost for this Yanakagi's algorithm is like what I claim here. Why? Because just convince yourself that every value, regardless of its input value and output value, you can participate in at most Q binary joins, actually Q minus one, okay? And since every time this value participates in a join, it pays $1. So the total number of dollars paid by this particular tuple cannot be more than Q, right? And hence the result. Okay. All right. So that's everything I have for today. Thank you for coming. Okay. And by the way, next week there will be no